So today we'll be discussing Newton's method. So Newton's method is used to approximate the roots of the function when it's not so easy. Like when the equation is y equals the square root of 5x, for example. It's very hard to find the roots just like that. So what we have to do is we have to use Newton's method to approximate these numbers. So the way we do that is by using this formula. X of n plus 1 is equal to xn minus f of n over the derivative of f of n. So this is how we solve every problem. Now what these are called iterations. Iterations are every approximation taken and done again. So this xn is the previous value minus the function y value over the derivative. So the way we're going to solve this is by setting up a chart. The chart is set up in a way to help simplify this process. So we have n, fn, f prime of n, f of n over f prime of n, and the last one, x of n minus f of n all over f minus n. And so essentially what we're doing here is we have to get the numbers close enough that f of n's, when we subtract, they have to be close enough that the number is really minuscule, so we can say the approximation is as accurate as possible. And usually there's a given like set value of how close you want the accuracy to be. So the teacher might be like, make it 0.001 decimals difference, or 0.01, whichever. So let's work with the example here. Let's say our function is 2x to the fourth minus 3x cubed minus 5x squared plus 6x minus 4. So our first step in this problem will be to find derivative, which will be 8x cubed minus 9x squared minus 10x plus 6. So now you're wondering, Musa, where do we start? So usually what you can do is you can graph the function and see a number that's most closest to. Or if that's not given, you have to kind of use common sense. But you can pick any number you want to start with. You'll get the answer eventually, but by picking a closer number, you'll get the answer faster. So if we graph this, we'll see that the x values are around 2.1 and negative 1.63. We're going to work with the 2.1 for now, and you guys can work the rest later. It's just an example. So we plug in 1 for, so this is our first iteration, so we write 1 for the n. Then we plug it into our function. So you plug in 2.1, you can put it into a calculator, and we get negative 2.3368. Oh, I left out the function. I left out the x. That's also comes before the n. And will come over here. X. This is really important because this is what you subtract your next step with to see how much the difference is and to see that test the accuracy. So then we plug this 2.1 into the derivative, and we get 19.398. And we put the calculator again to divide it, and we get negative 0.120, and then 2.22047. So now what we do is we take this number and we plug it back. We make this our new x value, 2.2040. We plug it back into the function. We plug this new number back into the function, and we get 0.44587. Then we plug it into the derivative, and we get 27.0046. Then we divide it, and we get 0.0165.4. and then we get 2.2039. And now we start this number with this number. We see that the difference is very minuscule. It's only it's 0.01. So for us, this will satisfy our conditions. And then to find the equation of tangent line, what we can do is we find we use this number to find the x value. So 2.2039. We plug this into our derivative to find the slope, because that's what the first derivative gives us, and we get 25.8841. And finally, we plug this back into the first function to find our second y value, and we get 0.00641. Thank you for watching this video.